Hi guys, so this is Nicole and Alex, and today we'll be working on the large vat with the saltwater solution problem. So part A asks us to write an equation for the line tangent to the graph of A at t equals 10, and then we're going to be using approximations to find the number of pounds of salt in the vat at t equals 12 minutes. So the first thing that we want to recognize is that when we plug things into the slope formula, that t equals 10 minutes is going to be our x1 value. 50 pounds is going to be our y1 value, also known as A, because it's the number of pounds inside of the vat. And dA over dt, which is a derivative, is going to be our m, or our slope. So now we know that dA over dt is equal to 6 minus 0.02 A, and we already know that A is 50 pounds. So if we plug that into the equation, we get dA over dt equals 6 minus 0.02 times 50. And when we solve for that, it equals 5, and 5 represents our slope. So now we're going to write the equation of a tangent line, which is y minus y1 equals m times x minus x1. So now all we have to do is start plugging in values. So y1 is going to be 50, so we have y minus 50. Our slope is 5, and our x1 value is 10. So now we're going to bring back the A of t equation, and we're trying to approximate the value of 12. So A of 12 is going to be equal to the simplified version of the equation of a tangent line. So we get 5 times 12, since that's the time that we're approximating for, minus 10 plus 50, and 50 we just move over from the y minus 50 side, and we get 60 pounds, which is the number of pounds in the vat at 12 minutes. Okay, now we're moving on to part B, and our job is to show that the equation on the top left, A of t equals 300 minus 250 e to the 0.2 minus 0.02t, satisfies the differential equation from part A, which is dA over dt equals 6 minus 0.02a, with the initial condition that we see on the top right of A of t equals 50 pounds. So the first thing that we want to do is rewrite under A of t that A of 10 minutes is the given equation. And at this point, we want to plug in the t value as 10, and we see that they cancel out. So all that we're left with is A of 10 equals 300 minus 250. And if we solve for that, that equals 50, which is proving the initial condition that we see on the top right. So the next step that we want to do is write dA over dt equals negative 250 e to the 0.2 minus 0.02t power. And we're going to multiply this by negative 0.02. And we're getting negative 0.02 from the differential equation that we have from part A, and it's just rewriting the equation. And then the next step that we're going to do is just simplify it down, and we get 0.02 times 250 e to the 0.2 minus 0.02t power is equal to 0.02 times 300 minus a. And if we just simplify that further, we get 6 minus 0.02t, which is verifying that the initial equation of A of t satisfies the differential equation from part A. Okay, so now we're on to part C, and in part C, we're given that the depth of the solution of the vat is modeled by the equation we see on the top left, which is dH over dt equals negative k times the square root of h. And in this problem, we're given a bunch of pieces of information, and they are that the depth of the solution is 16 meters at the time t equals 0, and it's also 4 meters at the time t equals 30 minutes. And what we want to do in this problem is find h of t in terms of t. So the first thing that we want to do is, in reference to the differential equation that we got in the beginning, is rearranging the problem so that dH and h are on the same side and dt and k are on the other side. So what we want to write is 1 over the square root of h times dH equals to negative k times dt. So here we see h's are on one side. The next step is that we can find the integral of both of those sides. And when we find that, we get 2 times the square root of h equals negative kt plus c, because we don't know what the constant is. So now we're just going to do a bunch of rearranging, and we will get that h equals negative kt plus c squared. And now we're going to plug in the given information that we got in the beginning of the problem. So we'll start off with 16 meters at the time t equals 0 minutes. So 16 is h, and that equals 0 plus c squared. 0 because anything times 0 is 0. And then we get c squared equals 16. And then obviously c is going to be 4. Now we're going to be working with the second piece of information we got from 4 meters. So we're going to be using the same equation that we got, which is h equals negative kt plus c squared. So we know in this example, 4 is going to be h, and t is going to be negative 30k. So we get 4 equals negative 30k plus 4, and the whole thing squared. When we solve it further, we get 2 equals negative 30k plus 4. And if we move 4 to the other side, divide by negative 30, we get k equals 1 over 15. So now we're going to try to combine all of these into one problem. So we're going to be using h equals negative kt plus c squared, and we're going to be plugging in the values that we got. So h of t is going to be equal to the k value we just found in the last step of negative 1 over 15t. And then we're going to be adding 4 to this value because 4 is the c value that we found in the initial equation when we were using 16 meters. So the equation that we get is h of t equals negative 1 over 15t plus 4, the whole thing squared, and that's the value of ht in terms of t.
And that is how we solve the large vat problem. Thanks for watching.